Hey guys, I thought I would give you a demonstration of how to complete the multiple regression exercise. So I'm here in the GitHub repository for this assignment, this multiple regression. I'm just going to download the files for this assignment in a zip file, and then open this up and extract it. Click in there in Windows and hit Extract All. Then you can extract that. And that should show you your files. And as usual, you want to open up the answer sheet for the steps to complete the assignment. All right. Just a word about these answer sheets. You're going to notice there's going to usually always be three main sections on these. There is some stuff about the study information. We don't have a lot on these assignments to answer in here, but I do include it with each assignment because I want you to be aware that any analysis is usually part of a study or part of a larger purpose. And so you really need to think about the background of what you're trying to accomplish with that analysis. And so I leave that information there so you can read through it each time and think about what might be the purpose of an analysis like this. So you'll see there's a heading study information. You read through the comments and things that I've posted there. Field, the text we're using for this class in this assignment gives some description of the study purpose, and you'll see that in the field book. And I would encourage you to go read through those sections to see what the variables are and what he's intending with those. And then you're going to see a section about the data set. And we will be looking at this, of course. This is looking at what are the variables in the data set and do they have any problems, and things that you ought to be considering when you're looking at a data set to do analysis. And you want to think about this every time you do an analysis. Have the data been cleaned? Are they accurate? Are there any problems? And because the results of any analysis are going to be meaningless or misleading if you haven't done these things before you actually conduct your analysis. So we're going to go through some of these steps when we're looking at our data set before we do anything. And then there's going to be a section about the test information. And I see here I forgot to change that to, let's enable editing, and forgot to change that to multiple regression. So, and then we're going to go through and do the steps to conduct our multiple regression in Jamovi. So now that we have our files downloaded, then we can go to the dataset information, and we're going to open this sales.save dataset in Jamovi. So I'm going to open up Jamovi. We're going to go to the File menu, Open, Browse, And this is in my downloads folder. And there's my .sav file. If you recall from previous assignments, the .sav file is an SPSS data file. You can use several different types with Jamovi, but that's one of them. Okay, so here are our variables, and I'll let you look at the sections in the field text to see what these are and what they're supposed to be. But we just want to make sure that the levels of measurement are correct in here. So we see these adverts. I think this is the amount of money spent on advertising, and that's a continuous variable. That looks correct. If we go to sales, that's also continuous, and that's set correctly. If we go to airplay, that is continuous, and that's set correctly. And rating on image. And normally I would call a scale of 1 to 10 ordinal level of measurement, but for the purpose of this assignment, he created this as a continuous variable, and we're going to go ahead and use it. When you're getting to close to 10 categories and above in ordinal data, it's kind of a gray area in statistics. You'll see it, used as ordinal, and then sometimes you'll see it used as a continuous variable. So just kind of highlight some of the challenges of statistics in some of the gray areas. So that looks good. We should make sure that we don't have any problems with missing data or outliers. And you'll see we do have a good, we have 200 observations here, and we don't see any glaring problems just looking at it, but we should get some descriptive statistics. So we're going to go to Exploration, Descriptives. Since these are all continuous variables, then we can just select them all and get our descriptive statistics at the same times. These are not categorical, so we're not going to worry about frequency tables. We're going to go ahead and leave mean and medium checked. We definitely want to see our standard deviation. We can leave minimum and maximum, that's okay. We'll always want to see counts and if we have any missing data. We'll go ahead and look at skewness and kurtosis and get a Shapiro-Wilk test for normality. And plots for continuous variables, we would always want to look at histogram and box plot. So just reviewing our descriptive statistics, we can see that we have no missing data. We've got our means and standard deviations. You can see these standard deviations are fairly, for adverts, it's fairly wide compared to the mean, so these are fairly spread out. Sales, not as spread out as adverts, but also still fairly spread out. Same thing with airplay, and images a little more clustered together. We've got minimums and maximums there. Nothing looks crazy or like just a nonsensical value. Skewness, and often when dealing with normality assumptions, skewness is what we worry a little bit more about. And I typically like to look at skewness divided by standard error of the skewness and see if that value is greater than 2. We can see for adverts that it is. So this is positively skewed, which means it's right skewed. Sales, that's not more than 2. Airplay, that's not more than 2. And image, that would be more than 2. And this one is negatively skewed, which is skewed to the left. And for normality tests, we can see a p-value for Shapiro-Wilkes. For adverts, it's significant, which we're not surprised about because of looking at the skewness that we looked at before. Shapiro-Wilk, that still came up. When this looks at both skewness and kurtosis, we see it is significant. airplay is not significant and image is significant, meaning that our data distribution differs significantly from a normal distribution. Plots, adverts, this is skewed to the right. We're not too surprised about that. There's a couple outliers there. That's something I would definitely go check if I had collected these data myself, double check that they weren't errors. I don't have any reason to exclude those from the analysis, however, so we won't be doing anything with those outliers on adverts. Sales, these look fairly normally distributed, might be a little platycritic. Airplay, not too different. There is one outlier up there. And image, we do see we have a few more down towards the bottom and a couple outliers on that one. So this is where you might, think, well, if I do have some issues with normality, do I have problems in this data set? And we do have a large sample size, so we're probably okay. And we'll just use it how it is right now. So that looks good. So on our answer sheet, we've got our variables in the data set, which we have listed in our output. Things that we would look at with accuracy, I have listed out there that you would go look at. We're not going to do any additional data manipulation here. Didn't have any issues with missing data. We did have a couple outliers, but we have large data sets, so we're going to leave those in the analysis. And if you were writing this up, you would want to think about what descriptive statistics do you want to put in your final report. I'm not going to do anything with that for this assignment. So test information. We are going to try out the Jamovi module StatCat. And so let's go make sure that you have that installed. If you don't already, I do have it installed, and I've shown that on a previous video, but if you didn't, you'd go to Modules, Jamovi Library, and scroll down through the available modules and install them if they're not. So I think I'm good with StatCat right there. So we'll go to StatCat, Relationship Prediction and Group Comparisons. And we know we're trying to predict sales, so I'm going to put sales in the dependent box. And I know I'm using adverts, airplay, and image as our independent variables. And you'll see that StatCat recommends a linear regression. And it is, StatCat does give us some scatter plots to look at. Here is sales and adverts, and here is sales and airplay, and here is sales and image. So that's a useful tool when you're trying to figure out what tests you could potentially use. So that is something that we can take advantage of and should get a little familiar with using. So anytime we're doing a regression, we need to do some assessment of our predictor variables, and scatter plots are a great way to look at some of the things that we need to. So we're going to go to Analyses, Regression, and Correlation Matrix, and we're going to go ahead and get all of our variables, and we want to flag significant correlations. And let's go ahead and get a plot. And let's go ahead and just have them put the statistics in with the plot. That makes it really easy to look at. So one of the things that we are concerned about is multi-collinearity in our predictive variables. So ideally what you want is to have predictor variables that have a strong relationship with your outcome variable. And in this case, sales is the variable that we're most concerned with as the outcome variable, but not too strong a relationship of the predictors with each other. And so usually what you're looking for is correlations of 0.8 and above. So those are pretty high correlations. So if we look at airplay with adverts and sales, or well, we really care about adverts, we can see it's 0.1, so it's not too high. Airplay and adverts, and image and adverts, also not too high, and image and airplay, 0.182, also not too high. So we don't have any problems with multi-collinearity, or we wouldn't anticipate any with this. And we do see here in the scatter plot that adverts and sales has a fairly strong relationship, as does airplay and sales, and image and sales has somewhat strong, and you can say image with the other two variables also not too strong. So we don't see any problems with multi-collinearity, and we don't see any problems with curvilinear relationships here. We could have some potential issues with homoscedasticity. Homoscedasticity is that the spread in the relationship is similar between the two variables at all levels of both variables. And you can see here on adverts at the low end that with sales, there's quite a spread here in sales at the low end of adverts, but there's not much variability in sales at the high end of adverts. So that might be a potential issue. We could consider doing some transformation here, but we're not going to worry about that for this assignment. Similar thing with, well, that's probably good enough for what we're looking at for this. So in my sheet where we're looking at, of course, we're going to be looking at a multiple regression, and we're going to be using sales as the outcome variable and adverts, airplay, and image as our predictor variables. So we're going to look at some of our assumptions that we would want to consider for doing a multiple regression. So one of the first ones listed by field is that the outcome variable should be continuous. And we already looked at sales, and it is. So we're concerned about our additivity and linearity. We did not see any problems with nonlinear relationships in these variables with the outcome variables, so we should be okay with that assumption. A normally distributed sampling distribution. When we have large samples, we're usually okay with that because of the central limit theorem. When you sample multiple times, the variable of interest will be the samples is going to be normally distributed around the mean in the population, even if it isn't necessarily normally distributed in the population itself. We're going to look for normally distributed errors. We'll talk more about that later in the semester, so we won't focus on that too much this week. And if we had small samples, we would be more concerned about the data being normally distributed, but here we have a large sample, so we should be okay because of the central limit theorem for meeting this normally distributed sampling distribution assumption. Homoscedasticity, as we discussed, there is an issue with one variable, but we're going to go ahead and move forward. We do have a large sample size, but you could look at doing a transformation potentially. Independence of observations, unrelated errors, we'll look at that a little more later in this semester. This is also known by the study design. We know that we did not have, we would know that we didn't measure, groups of similar people that had some obvious relationship where we weren't looking at the same people at multiple time points. Those would be causes issues with our related errors. Predictors are uncorrelated with external variables. Field talks about this. I would encourage you to read the chapter on regression, and what this basically is there's no important predictors that are left out of the model. That would be if any of our predictors are correlated with something else and that's not in the model, then that could cause a problem with the model, and we don't have an issue with that here. And then the assumption that predictor variables must be continuous or categorical with two levels, and these are all continuous variables, so we're okay with that. We did have some outliers in there, and that might be something to look at with our model, and you might, like I said, you would correct it if you could, or consider if they're having undue influence, and we will look more later in this semester at assessing some of those things. And then multi-collinearity between predictor variables, which we wouldn't anticipate that we'll have any issues because we looked at the correlations and none of them are 0.8 or above between the predictors. And predictors should have variation. There's no variance of 0, and we do have that in our predictor variables. So now we're going to go through and get our multiple regression, and we're going to go through our steps of null hypothesis significance testing. So the first step in that is to decide what are our null and alternative hypotheses. And as we started to learn last week, regression, there's actually several that we're looking at. We're concerned about the model overall, and so there's a null and alternative hypothesis for a test of the overall model. The null would be the model is not significantly different than an empty model, which is just the intercept, and the alternative would be the model is significantly better, or there's significant difference between the empty model and the model that we're looking at. And then we're going to look at the parts of the model, and the parts of the model are the intercept and the slopes of the predictors. So our null for our intercept would be that there is no significant difference between our intercept and 0, and the alternative would be there is a difference between our intercept and 0, or our intercept is significantly different than 0. And then for the slopes of each of our predictors, there's going to be a null hypothesis that there is no difference between the slope and 0, and the alternative would be there is a difference between the slope and 0, and there's going to be one of those for each of your predictor variables in the model. So in this case, we have 3 predictors. Each is going to have its own null and alternative hypotheses, and we're going to see in the output where that gets tested and interpret it. We typically use alpha 0.05 for these things, but there are situations where you wouldn't use alpha 0.05, and I do describe that a little bit here. So for the model overall, we're going to use alpha equal 0.05. For the model intercept, we're going to use alpha equal 0.05, and for each of the slopes, we're going to use, each of the predictor slopes, we're going to use alpha equal 0.05. This probably goes without saying in a lot of cases, but I do like to be explicit on what we're really doing. So now we're going to calculate our test statistics. So we're going to go into Jamovi analyses, regression, and linear regression. And our dependent variable is sales, and our covariates are adverts, airplay, and image. And we're going to go to the model builder, and we are going to do a hierarchical model like field does in his text. So we're going to do, we're going to add a new block, and we're going to drag airplay and image from block 1 to block 2. So we're going to say add a new block, and we'll add airplay and image into block 2. And assumption checks, we're going to get Shapiro-Wilk, excuse me, QQ plot and residual plots. So assumption checks, we'll go ahead and get QQ plot, and I think we got Shapiro-Wilk in our descriptives, and residual plots. And we'll look at some of these other things a little later in the semester. Model fit, we're going to keep R and R squared. I'm going to go ahead and get adjusted R squared, and we'll get an F test. And model coefficients, we'll get an ANOVA test, confidence intervals, and a standardized estimate. And this last part is new since the last time that I used Jamovi, and this is actually a great addition, and we'll look at this more later on in the semester, but let's go ahead and just check these boxes and get these numbers. So this bottom part, what this actually does is it's going to save some numbers in the data set for us. So if we went back to data, you'll see we now have residuals here saved out for us. We won't really look at that too much this week, but we will later on in the semester. So now that we have got these things, we're going to go and pull some information out of our output and take a look at it. So first we're going to look at our overall fit of the model. So we'll go to the top of our linear regression and model fit measures. So we actually asked for 2 models. We asked for one with a single predictor and then one with our 2 additional predictors. And you can see that this tests our first model against an empty model where it's just the intercept, and we see that it is significantly different. So our R value would be 0.578, and typically when I'm working with multiple variables, we will look at the adjusted R squared rather than the R squared, because this does an adjustment for multiple predictors, and we see that we have an adjusted R squared of 0.331, and that interprets to the amount of variance, what percent of variance is shared between the predictors and the outcome variable, and so that would be 33.1%. So our R value for our single model, and we'll actually look at our final model for getting our numbers. I probably should have said that in there. All right, so On our final model, R would be 0.815. Adjusted R squared would be 0.66, which means that our final model predicts 60% or shares 66% of its variance with the predictor variables. F is 129.5 with a p-value of less than 0.001. And in the answer sheet, I do ask you, is Model 2 significantly better than Model 1? And the answer to that is yes. The adjusted R squared is higher, and our p-value is definitely significant. So adding those extra predictors does give us more prediction over the outcome variable than the first single predictor. And we see some model-specific results. We can choose which we're looking at. Here it gives us Model 1 and Model 2. If we just looked at Model 1, that would only have our single predictor variable, but we're interested mostly in our final model. So what is our unstandardized coefficient for adverts? And we're going to come down to our model coefficients to find those. And here's our intercept. So on the answer sheet where it's asking for our unstandardized coefficient on the intercept, that is down here in the model coefficients. And we see it's negative 26.6. For adverts, our unstandardized coefficient is 0.0849, probably round that to 0.085. For airplay, it's 3.37, and for image, it's 11.8. And it asks which predictor variables are significant predictor of sales. So if we look at our tests of our model, of our predictors, we see that for adverts, it's a significant predictor. And we see that for airplay, it's also a significant predictor as p less than 0.001. And for image, it's also a significant predictor. And I ask you a question: which predictor variable is the strongest predictor? So we really can't tell that by looking at the raw unstandardized values. We really have to go to our standardized estimates to be able to do that, because these are all in different units. Image, that was a rating scale. Airplay was, I think, time in minutes or something like that. And adverts was in money. So these numbers don't really compare with each other because they're in different units. But recall, if we standardize a score, then we're in standard deviation units and they are comparable. So which of these values is the highest? And we see that adverts is 0.511, airplay is 0.512, and image is 0.192. So we see that the strongest predictor in sales is airplay, and the weakest one is image. So these standardized estimates are really useful for comparing the variables with each other and determining which ones are the stronger and weaker predictors. All right, and then some assumption checks. We can see our QQ plot is between the quantiles and our standardized residuals. It looks pretty good. And we will talk more about residual plots later in the semester when we talk about regression diagnostics. So as you can see with regression, there is a little more to consider. There is our model overall, and there are our parts of the model. And it really, all studies, there's different studies which focus on different things. Sometimes they're more concerned about the model overall, and sometimes they're concerned about the parts of the model. Sometimes they're concerned with both. So there's a lot you can do with regression, but it's really nice that you can. It's a very flexible framework, and there's a lot you can do with this when looking at relationships between variables and trying to decide what things are good predictors. So I hope that helps you complete the computer part of this assignment. And if you have questions, oh, okay, one more. I was missing part of the final parts here. So conclusions about the null for the model overall and parts of the model, everything was significant, so we would reject the null on all of those things. I do ask you, what is the prediction equation for multiple regression? So in a linear regression, we can actually get an equation to predict sales from adverts, airplay, and image. So what we would do with that is we would say our predicted sales is equal to our intercept, negative 26.6, plus 0.085 times the value for adverts, plus 3.37 times the value for airplay, plus 11.09 times the value, or 11.1, I'd probably just round to one decimal place, times the value for image. And that would be our prediction equation. And Field does give a nice description in the chapter about writing up results. I'm not going to make you write those up, but be aware he gives some good recommendations about how to write the results of that. So you do want to save your Jamovi, our OMV file. So we can go here and do save as, browse to make sure we're in the correct folder, and we see that we are, and you can leave it this name or call it whatever you want and save that. And we also want to save our output, our PDF. If we right click in the output and go to all and export, and we can go to browse again and make sure that we're in the right folder, and we can say week 8 output and save that. All right, that is the Jamovi part of our assignment, and we're going to open up our R Markdown file in RStudio. So we're going to go to our folder, and we're going to go to our rmarkdown.rmd file, and we want to open with RStudio. All right, so you'll read through this as you go. Here's our packages. If you've done these assignments, these should go fast, and we won't have to install anything. If you haven't installed these yet, then this will take a few minutes to run. But we'll let that do its checks, and we see that I have them all installed, so it goes pretty quick. And we're going to load the packages into memory so we can use them by running the library command with each one. And there's some information about multiple regression. Here we're going to open up our data file using the Rio package, and this is our album sales file. We'll run that one, and we can see that we have our data set variable that came up, and if we click on that, it will show us our variables with the data in them. So that worked pretty well. And we can get the R code from an analysis that we did in Jamovi. And I can show you that again. If we go to Jamovi, and I don't think I asked you to run this in the assignment, but just so you're aware, you can see the R code for the analysis that we got. If we click on those three little vertical dots and check the box for syntax mode, you can see that there's our correlation matrix. Let's see, we should have our code that was used to get our descriptives, and looks like StatCat's part of that package, and we'll give you some information from StatCat. And finally, there's the Jamovi linreg function and the settings that we use to get this output. I'm going to go ahead and turn that off, but just so you realize, you can get the R code that would be used to get the analysis that we worked on. All right, a lot of times in R, they will calculate linear models using the LM function. And so we're going to go ahead and give that a try. I do have some code here for you to run. We're going to look at some scatter plots. Like we did in Jamovi first. And there's our plot, kind of some funky looking output. I know some people have been getting plots over here in the plots window, and if you, I think there is a setting up here, this little drop down by the gear. You can either choose chunk output inline and chunk output in console. I think this chunk output inline should be selected by default, but if you wanted your output to show up in the thing, I think that's one thing you could check. If that is checked and it's not, then maybe we can troubleshoot. But I think that is one thing that you can check to make sure is checked to get your plots out here in your output. And this is looking at a single scatter plot. We're not going to worry too much about it, but it is something there that you can do. Now we're going to go ahead and get our model, and we'll see what the LM function gives us in R. And you can see, we can see some coefficients there. Not a lot of information yet. In an R, we put our model into a variable called model, and there we're going to use this summary function on model and see what it gives us. And we got some residuals. You can see here's our coefficients, and this will compare with the Jamovi output. Get Jamovi back up here. And so you see the model coefficients table in Jamovi has intercept, adverts, airplay, image with estimates and confidence intervals and p-values and standard estimates. And you can see that our numbers from the linear model, there's our intercept and adverts, airplay, and image, all pretty much match with the output that we get in Jamovi. I find the Jamovi output a little easier to read, but you can go see the parts. You will notice, though, that R did not give us any standardized residuals, and I always like to look at those. So there is a way to get your standardized residuals, and it's using this scale function to standardize all of the inputs, and that will give us standardized outputs. And if we run that, we can see that the values that we have here, you'll see we don't have an intercept on our Jamovi output. It's the standardized is equal to the mean, and the mean is a mean of 0. And you'll see this is 5.5 times 10 to the negative 17, which is about as close to 0 as you can get. So for all functional purposes, that is 0 because that's the mean. But you'll see then we have our standardized 5.1 exponent negative 1, so that's going to move that decimal over, so it's going to 0.5108 and 0.512 and 0.191, 1917. So you'll see those match with our standardized estimates. So it does take a little extra work to get those from linear model and R. And then I do have an example of the Jamovi command there that you can run in RStudio, and you'll get your output here, and it matches pretty much. So that's an example of how to do it in R and RStudio. And last of all, we're going to knit this document for our markdown. So we're going to click next to knit and knit to markdown. And this is going to run. It takes a couple minutes. Probably not a couple minutes, but it does take a few seconds to go through its thing. You can see it's adding some files in here. And here's my .md markdown. Pretty sure that those saved, so I can just close that. And now if I go to my folder, you should see there's my plain markdown file. I have my OMV file, and I have my PDF. And to turn these in for the class, we're just going to want to go to our repository, our GitHub repository, add file, and upload files. And we can either choose the files or drag them to our thing. So I'm going to drag those 3 files, markdown and output PDF. And then you will go down and click commit changes. I'm not going to save that, so those aren't part of the repository. So there is a demonstration for how to do a multiple regression in Jamovi and in RStudio. And I'll talk to you later.